Hi, everyone. Today we're talking about torque and moment of inertia. Now, first, let's talk about how torque and moment of inertia are going to help us solve new problems. So we'll review Newton's second law of motion in regards to torque, right? This says torque is I alpha, okay? And now we're going to use that here. We have a bicycle wheel that has a diameter of 64 centimeters and a mass of 1.80 kilograms. The bicycle is placed on a stationary stand on rollers, and resistive force of 120 newtons is applied to the rim of the tire. So this is just like a stationary bicycle. Assume all of the mass of the wheel is concentrated on the outside radius to give the wheel an acceleration of 4.5 seconds to the negative 2 power, or radians per second squared. What force must be applied by a chain passing over a 9 centimeter diameter sprocket? So let's draw this. We have a wheel, center, okay, and the diameter of the wheel is 64 centimeters. Then we have a sprocket with a diameter of 9 centimeters. Okay. Then the rollers down here are going to give a resistive force of 120 newtons. But this sprocket is going to oppose that with an acceleration of 4.5 radians per second squared. But remember, you don't write the radians. Did I get everything? I think I did. Oh, and then the mass, right? Mass of the wheel is 1.8 kilograms. And it says that this is what all of the mass of the wheel is concentrated on the outside radius. So that means that we have a different moment of inertia than if this were just a normal cylinder, right? That means that we have a moment of inertia of mr squared. Okay. So we've got I equals mr squared. We know torque equals I alpha, but we're also going to have a summation of torque. Okay. We're going to have the resistive torque, and we're going to have the torque of the sprocket. So the resistive torque is the force of that resistance times the radius of the wheel, right? Because it's acting out on the wheel's radius. The torque for the sprocket is the force that we're looking for, right? What force must be applied? That will be times the radius of the sprocket. We're assuming that this is 90 degrees, right? All of these forces are going to be tangent, so we will ignore the sine theta for now. We're going to consider it 1. So if we have the torque of the sprocket, right, is, here, I'll continue this down here. Torque of the sprocket is Fs Rs minus the torque of resistive force, Fr Rw, and that will equal I alpha. I'm actually going to substitute that I out because we know that that is m r of the wheel squared times alpha. So now we've broken it down into the components that we know, and we just need to solve for the force of the sprocket. Now we're not considering the moment of inertia of the sprocket here. We are just considering the moment of inertia of the wheel. So if we solve for the force of the sprocket, you have mr of the wheel squared alpha plus resistive force, radius of the wheel, all divided by the radius of the sprocket. And we have all of this, right? We've got 1.8. Radius of the wheel would be 0.32 meters. Okay, that's half of 64 centimeters. That will be squared, and then we multiply that by 4.5 for that seconds inverse, double inverse. And then we've got the resistive force, 120 times, again, 0.32 meters. And then we divide by 0.045, right? 4.5 centimeters or 0.045 meters. Plug that all in your calculator, okay, and then you will get that the force that is exerted on that sprocket must be 872 newtons if it is going to be a tangential force. So that's how the Newton's second law of motion can work in our favor by using the moment of inertia. Now, the question, can you fall faster than g just by sheer gravity? Okay, we've got a uniform rod of length L and mass m rotating at a frictionless pivot. Calculate the initial angular acceleration of the rod and the initial translational acceleration of the right edge. So here we're going to use torque equals I alpha. But here we want alpha. So alpha will be torque divided by the moment of inertia. Torque in this case, we will say that the force is mg, and the radius for the torque is going to be L over 2. Right? So we're assuming that mg is acting at the center of mass of the rod, and that is where the force is going to be located, so that'll be our r. Again, we're assuming tangential, so sine theta would equal 1. Our moment of inertia, this is a rod being rotated about its end, so this would be ml squared divided by 3. So when we put this in, we have, I'm going to multiply by a reciprocal here. So we'll do mgl divided by 2 for torque. Then I'm going to multiply by the reciprocal of the moment of inertia, 3 divided by ml squared. You can see already that the masses will cancel. One of the L's will cancel, and that will give us 3g divided by 2L for the, what is that? Angular acceleration, right? Yeah, angular. We're doing tangential next. So that's the angular acceleration. 3g divided by 2 times the length, which doesn't really have a whole lot of meaning to us, but let's get to that tangential acceleration. Okay, this is how fast the end of that rod is going to accelerate. This is the interesting part. So that is alpha times the radius, right? But the radius here is not from the force to the pivot like it was for the torque equation, right? 2 different radii when you talk about force and radius for torque and alpha times radius for acceleration. Here, this is the distance from the pivot to the point on the object we're wanting to analyze. Because remember, the tangential acceleration is different at every point along the radius. So we need the radius out to that point. So the radius here will be L. So we take our alpha, 3g divided by 2L, multiply that by L, and now we have something we can understand, 3/2 g. So that means that as this rod is falling just due to gravity, the end of the rod is actually accelerating at more than g, more than 9.81. It's actually accelerating 150% of g, or 3/2 g. So, which is interesting, right? Now we can also look using this equation, at equals alpha times radius. At what radius along that rod is the acceleration just g? So if we take alpha t divided by, at divided by alpha, we could get the radius for that. So if we take at, which is 3g over 2, and we multiply by the reciprocal of alpha, which would be 2L divided by 3g, right? Let's see what cancels. 3g's cancel. The 2 cancels. Whoops. Oh, I know what I did wrong. If we want g, right, for our acceleration, that's what I did wrong. G divided by alpha, which is 3g over 2L. So I'll do that, the reciprocal, right? G over 1 times 2L divided by 3g. Sorry about that. Had a brain fart there. So the g's cancel. You then get 2/3 L. Okay? So 2/3 along that length, that's the point in that radius that you're actually going to have a g acceleration. But any further than that, and you're accelerating faster than g, and that's going to cause some issues on that structure, which is what we have right here. Now, the next question asks us, why does this smokestack break in the middle, right? So if we're looking at this, right, we just established that 2/3 L, it is going to fall at a rate of g, right? But at the end, at the full length L, it's accelerating at 3/2 g, which means that all along this smokestack, okay, before it had broken, at every point you're changing your acceleration piece by piece, right? Which means that there will be a certain point that this is going to have to break because there is more acceleration here than the acceleration down here. Okay? As that acceleration increases as you move along the length of the smokestack, that's going to cause a force within the smokestack that its structure seems to not be able to handle. It's no guarantee that it would break, but here we can see that with such a long object, there is going to be a much greater acceleration at the end than near the pivot, and that can cause structural damage. So that is why the smokestack breaks. All right, for our next problem, a bit of physics magic. This one's a doozy, so it's going to take a lot of drawing to get through. A board is hinged at one end and has uniform density. A light cup is placed near the end. Light, meaning massless. Derive an expression to show an angle for 35 degrees, 35.3 degrees allows the cup to actually catch the ball. So we are going to work off of 2 points. Okay, first we need to establish that that is the theta that they're talking about, because once we do our torque, okay, we've got mg that is causing the torque, right? That has a different angle, okay? This is the radius for our torque, and this we will call angle phi, okay? That creates this angle and this relationship that we've got phi here and theta here. We'll come back to that triangle in a minute. Now, when we talk about tangential acceleration right here, okay, and g here. I drew that too long. Oops. So g here, this is also angle theta. We can show that if I move that phi in there. We can show that if there were a tangent right here, okay, we can also say that there is an acceleration here. This is the same angle theta as the other theta on that other side, right? So we have these two circles that we're going to deal with. Okay? The AG triangle, and did I say circle? The AG triangle and this theta phi triangle. Now on that GA triangle, we want to note that cosine theta is g divided by the tangential acceleration, which means that the tangential acceleration times cosine theta will equal g. And if that's true, we are successful in catching the ball. All right, now that we've got that drawn up, let's start working through our math. Okay, so we know that torque equals I alpha, and our torque here is caused by mg. The radius for that torque, okay, we established that over on our drawing. That's only to the center of mass, right? Gravity works on your center of mass. So that is at a radius of L/2, okay? And that is not perpendicular to the radius. That is at an angle phi. So your torque, Fr sine theta, that theta we're going to call phi here because of our relationship in that drawing. Now, mg L/2 sine phi, that will equal I alpha, we can also know that this is a rod rotating on its end, right? So that will have ml squared over 3 for its moment of inertia. So then we have ml squared over 3 times alpha right there. Now, what we're shooting for, right, is this relationship right here. But we need tangential acceleration to get there. So let's get there. Let's solve for alpha. You have, I'm going to multiply by the reciprocal. You've got 3 over ml squared. That gets rid of that guy there. And then that is multiplied by mgl over 2, right there, times sine phi. And that equals alpha. Now you can see that the m's will cancel. One of the l's will cancel. And this can simplify to say we've got, let's see, 3g over 2l sine phi equals alpha. Now, we can also say, to get this from from angular acceleration to tangential, right? You've got the equation AT is alpha times radius. But that's a different radius. Don't forget that that radius is the radius from your point all the way back to the pivot, okay? Because tangential acceleration is different for every point along a radius. So that is a different radius than we've been dealing with. So that radius would be L, because we're dealing with the cup and the ball are on the end, right? So we take our alpha, which was 3g over 2l sine phi times L, and that will cancel with the L down below, giving us 3g over 2 sine phi. Now, we are going to use that tangential acceleration with our cosine theta. But we're trying to solve for theta, right? We're trying to find the angle that this is going to work. If we throw in a phi with a theta, you're doomed. You're not going to be able to reconcile that phi in your equation. So that brings us here. Okay? If we look at this relationship, okay, this relationship shows that with a little trickery, sine of phi also equals cosine of theta. Okay? So we can make that substitution down here to say that this actually equals 3g over 2 cosine theta. So that is our AT. Okay? Now I'll bring that relationship down from above. AT cosine theta equals g. We have to make that true. So let's find the angle that makes that true. Our AT is 3g over 2 cosine theta times another cosine theta will equal g. Now what we'll do here is we're going to solve this in terms of theta. So we'll solve for cosine squared. We've got cosine squared theta. Those g's will go away once you divide that over. Now you're just left with 2/3. Now this gets a little bit easier. Cosine theta is the square root of 2/3, meaning that theta is the cosine inverse of 2/3. And if you do that math, you're going to get something really close to 35.3 degrees. All right, that is all for this video, and we will continue on through chapter 10 in our next.